Hello everyone, good afternoon. I'm Rui Yezu from Department of Energy and Power Engineering, Tsinghua University. This work is under the direction of Professor Wang. The title of my research is Numerical Study of Differential Diffusion Efforts on Hydrogen-Enriched Turbulent Non-Premixed Flames. With the increasingly stringent regulations on carbon emissions, hydrogen as a zero-carbon alternative renewable fuel has received progressively increasing attention in propulsion and power generation engines. Hydrogen has the advantage of high energy density, potentially high combustion efficiency, low pollutant emissions. Based on this, the basic science center of the two engines have carried out research on principal configuration of combined cycle and high efficiency and zero emission advanced gas chamber, and proposed the steam diluted hydrogen enriched oxygen combustor turbine combined cycle. And the combustor is shown in this figure. Adaptation of hydrogen into fossil fuels with variable composition, referred to as fuel flexibility, is an important combustion design parameter. The hydrogen-enriched hydrocarbon combustion shows distinct reactivity and diffusivity, owing to the unique characteristic of hydrogen flames. This implies the significance of differential diffusion in accurately describing the hydrogen enrichment turbulent flame structures as revealed in many previous experimental and numerical works. Miracles studied in both hydrogen-enriched non-reacting jets and diffusion flames. They found that there is a good agreement between numerical simulation results and experimental data when considering differential diffusion efforts. And in low, moderate, or even high Reynolds numbers flows, differential diffusion can be important. And it also affects the temperature and the species concentrations. The previous studies have indicated the importance of differential diffusion, but they primarily focused on simple hydrogen-air diffusion combustion. However, for complex systems such as steam-diluted hydrogen-enriched oxygen diffusion flames investigated in this work, the differential diffusion efforts and its mechanisms influencing mixing and the combustion process requires further exploration. Furthermore, most research have qualitatively analyzed the differential diffusion, necessitating quantitative methods to investigate its impact on the mixing mechanisms and combustion characteristics. For the theoretical framework, the governing equations are as shown in following. In the species equation, the unresolved subgrid scale species fluxes are modeled by the grounded diffusion hypothesis. The effective mass diffusivity is the sum of species lambda and turbulent mass diffusivities, and similar to the species equation, the effective thermal diffusivities in enthalpy equation is the sum of species and turbulent thermal diffusivities. Different species have different Lewis numbers. As shown in this table, the species Lewis number of hydrogen is 0.29 and the Lewis number of methane is 0.98. Hydrogen diffuses faster than methane. In this study, we use one equation ID viscosity model, which the turbulence viscosity is computed using subgrid scale kinetic energy. For combustion model, we use a partially stirred reactor, which consider both turbulence and chemistry timescale. As we mentioned before, this study investigates the impact of differential. Okay, sorry about that. As we mentioned before, this study investigates the impact of differential diffusion on steam-diluted hydrogen-enriched oxygen mixing and combustion process. By simplifying the model of combustion chamber, the schematic diagram of a triple coaxial nozzle is obtained as shown in this figure. A mixture of hydrogen and massive fuel blend is injected into the inner circular jet, while steam and oxygen are injected into the middle and outer jets. The numerical simulation was carried out on a two-dimensional grid of 80 multiple 360 mm with a minimum grid of 0.5 mm. Look at this table. Various parameters, including Reynolds numbers, hydrogen mole fraction, and steam volume fraction, are explored. ED is equal diffusion, and DD is differential diffusion. We consider non-reacting and combustion cases. The LES calculations are performed based on open form software with a modified version of reacting form by considering the different mass diffusivities in species transport equation and the non-unit release number in enthalpy equation. After this, the model assignment is first conducted on non-reacting jets in order to quantify the effort of differential diffusion. We introduced a factor Xi is based on the normalized concentration of hydrogen and mass. The definition of Xi takes on non-zero values only when hydrogen or mass ratio differs from its initial value in field. The left figure shows the ED and DD cases, the mean Xi distribution, as we show in this picture. In the case of equal diffusion, the mass diffusivities of hydrogen and mass are equal, and their distribution is exactly the same after normalization, and Xi is identical to 0. However, in the case of differential diffusion, because hydrogen diffuses faster than mass, it preferentially diffuses outwards, resulting in significant distribution differences. The Xi presents a negative value near the center line, and in the outer regions, Xi presents a positive value, indicating that the hydrogen concentration is relatively high. As the jet flow downstream, the differential diffusion effort gradually weakens, especially near the outlet, because the concentration distribution of each component tends to be uniform, and the diffusion process slows down significantly. Previous studies have identified the Reynolds number as a critical factor influencing the differential diffusion effort. This study quantifies the differential diffusion effort to investigate its mechanisms under conditions of moderate to high Reynolds numbers. A sustainable differential diffusion effort is evident near the nozzle exit across all Reynolds numbers. However, such effort diminishes downstream as Reynolds number increases. And as shown in this picture, presents the scatter plots of normalized hydrogen and mass at different R-divided D positions. The diagonal line represents the equal diffusion. With the increasing Reynolds number, the dispersion of points clearly much wider for the low Reynolds numbers. At positions away from the jet center, increasing Reynolds number leads to higher observed values of normalized concentration of hydrogen and mass due to enhanced injection of fuel mixture resulting from higher fuel velocities. The increased fuel concentration facilitates the ratio outwards diffusion, particularly in regions with significant concentration gradients near the nozzle exit, as shown in this picture, thereby strengthening the differential diffusion efforts. These findings emphasize the non-negligible role of differential diffusion efforts even under conditions of strong turbulence. And for hydrogen enrichment ratio and steam volume fraction, increasing them tend to amplify the differential diffusion efforts. Increasing hydrogen fraction enhances the ratio diffusion of hydrogen, thereby strengthening its influencing area, and the increase of steam volume fraction promotes the diffusion of fuel and steam and amplifies the differential diffusion efforts. Later, for combustion cases, varying chemical reaction rates also induce differences in hydrogen and mass distribution. resulting the differential diffusion factor we defined before cannot accurately describing the distribution differences. Therefore, a correction to the differential diffusion factor is necessary during combustion. Initially, in your macro simulations, inert steam is introduced to distinguish incoming steam in the system from chemically generated steam. Inert steam shares the same thermal and transport properties with steam, but do not participate in combustion reactions. Furthermore, relative to combustion products, intermediate species exhibit low concentrations, so we think local combustion products plus unreacted fuel approximate the pre-combustion fuel distribution. Then the revised differential diffusion factor C star is defined in the follows. And we compare the mean differential diffusion factor in non-reacting jets and diffusion combustion as shown in this picture. The left is non-reacting jets. The value range of differential diffusion factor in combustion is much wider in non-reacting jets. This is because the chemical reaction consumed fuel promotes the diffusion, thus strengthens the differential diffusion effort. And for flame structure, considering differential diffusion efforts decrease hydrogen concentrations and changes OH distribution, and the temperature near the nozzle exit as shown in this picture, the red line is much higher than the equal diffusion condition up to 400 K. With the increasing hydrogen morphism, significant reduction are observed in the negative C star region near the nozzle exit, while the positive C star region notably strengthens. Compared to MIC, hydrogen exhibits faster diffusion rates, and increasing the hydrogen morphism promotes the combustion of hydrogen near the nozzle exit. This promotes outward diffusion of hydrogen from the central fuel region, thereby reducing the size of central fuel zone. Simultaneously, rapid combustion of hydrogen near the nozzle exit diminishes oxygen concentration, thereby constraining the diffusion combustion of methane. As shown in this picture, under condition D3, the blue line with the hydrogen morphism equal to 0.8, the peak of the differential diffusion factor C star shifts towards to the center, with an increase in maximum position value and a decrease in the maximum negative value. And we can also observe with an increase in volume friction of steam, the flame rises, which weakens chemical reaction near the nozzle exit, and thus diminishes differential diffusion effort. As the flame further rises, there is no chemical reactions occur near the nozzle exit. Then it's similar to the non-reacting jets, thereby enhancing the differential diffusion effort near the nozzle exit due to the dilution by steam. In conclusion, the impact of the steam friction on the differential diffusion effort should consider both mixing process and chemical reactions. Finally, it's the conclusion. This study investigates the impact of differential diffusion on steam-diluted hydrogen-enriched oxygen mixing and combustion process. The reacting foam solver is employed and modified by considering the different mass diffusivities in species transport equation and the non-unit Lewis number in enthalpy equation. In this work, we introduced the differential diffusion factor in both non-reacting jets and diffusion flames. In non-reacting jets, decrease Reynolds number, increasing hydrogen morphism, and increasing steam morphism tend to amplify the differential diffusion efforts. For combustion cases, the rapid diffusion of hydrogen alters local composition and influences OH concentration and flame temperature. The increased hydrogen morphism promotes hydrogen combustion near the nozzle exit. The peak of differential diffusion factor C star shifts towards the center. and the impact of steam freezing on the differential diffusion effort should consider both the mixing process and the chemical reactions. That's all for my presentation. Thanks all of you for listening.
Maybe I need some information. I'm wondering if there are any experimental data to compare with your simulation. I mean, how can you prove your simulation are accurate?
Yes. In this work, they prove their simulation with their experimental data, and in my simulation, I do a similar structure as his work and use his experimental data.
Okay, so your simulation model is almost the same with this work, right?
Not the same. Not the same. I use my my simulation and his experiment data.
More questions? One quick question. So
Okay.
why do you observe the differential diffusion is so strong at high Reynolds number near the north axis, but not that strong at the low Reynolds number? Yeah.
In this picture, I explain it in this picture because the wait a minute. Because the high Reynolds number means the high velocities, and there means more hydrogen and must say injected into the computational domain.
The mixed fraction is the same, no matter with the velocity.
You mean mixture fraction?
Yeah, you measure this differential diffusion by the difference of mixture fraction.
Not the mixture fraction. Yeah.
I think it's fine.
Oh, okay.
Do you have more questions?